Hey guys, how's it going? All right, guys. Last topic in our sequences and series unit for Math 20-1, and the topic is called infinite geometric series. Okay. So guys, I remember the first time that I ever learned about this one is I definitely had a problem with that, and I thought, well, if you're adding something forever for infinity, well, how could you ever get an answer other than infinity? Okay. Until someone showed me this example over here. If you say 0.3 plus 0.03 plus 0.003. I keep adding this sequence for infinity. Well, the answer is going to be 0.3 repeating, which is the same thing as 1/3. Okay, so this is an example of what we call an infinite geometric series. So first of all, it's geometric because the common ratio, if I divide this by this, I get 0.1. And that happens for all the terms over here. Okay, and so if you keep on doing this forever, it's going to be 0.3 repeating, which is 1/3. Okay, so this sum for infinity equals this this fraction over here. Okay, so consider the geometric sequence: 1/1/2, 1/4, 1/8. So if you're looking at this sequence here, this is a geometric sequence. Tn equals t1 r to the n minus 1. So that means Tn equals 1 times 1/2 to the n minus 1, which is 1/2 to the n minus 1. So, guys, the next bullet over here, and this is really kind of like an intro to some of the stuff that we study in calculus. So, if you're in Alberta here with us, that would be our Math 31 course. You may learn this in university as well. But what I was talking about, so we're talking about the ideas of a limit. Guys, don't worry too much about the formal definition of a limit, but as n gets huge, okay, so for example, if I put in like, let's say an n value is like 1,001. That means, what's this going to be? Well, it's going to be 1,001 minus 1,000, so minus 1, which is 1/2 to the 1,000, which is 1 to the 1,000, which is just 1/2 to the 1,000. Well, this number over here is going to be like, I'm going to say, extremely close to 0. It's never actually going to equal 0, but it's going to be extremely close. 2 to the 1,000, guys, is going to be an incredibly massive number. 1 divided by that is going to be so close to this. So what we say, guys, is a limit is 0. Okay, so if you keep taking this sequence and you go forever and ever and ever, like if I just take this guy for a few more, like if you look at this decimal, what's 1 divided by 1,024 equal? Well, it's 0.0009765 ... So this is only the 10th term, okay, and it's 0.0009765. Well, if I do that to the 1,000th term, just imagine how close that is to be 0, okay? So the idea is, guys, if we extend n to infinity, I would say that this sequence over here is going to get infinitely close to 0. Okay, that's kind of a weird topic to think about, infinitely close to 0, but this is what we say. Okay, so for this sequence over here, if you take it to infinity, this value is going to get close to 0. So if we have 3, 6, 12, 24, what's the general term of this sequence? Well, we have Tn equals T1 r to the n minus 1 is 3 times 2 to the n minus 1. Well, if you look at this case over here, I'm just going to keep writing this sequence for a few more terms over here. Hopefully you'll see that these numbers over here keep getting bigger and bigger and bigger. So in other words, like, there is no limit. Or maybe you could say infinity. So what's different about these two questions over here, if we look at the previous example, the r value was 1/2. if you look at this example, the R value is 2. So hopefully you can see if I'm multiplying times 1/2 every time, my numbers can keep getting smaller and smaller and smaller and smaller. But if I multiply times 2 to get to the next term, my numbers can keep getting bigger and bigger and bigger and bigger. Okay, so if the numbers keep getting bigger, it can't have a limit. Okay, so example 30 says, under which conditions will a geometric sequence have a limit? So here's a condition that has to be met. If R is in between -1 and 0, -1 and 1, that's going to mean that you're multiplying times a number, which can give you a smaller and smaller and smaller number every time. Okay, so R has to be in between negative and 1. Okay. All right. So example 31 here. We have this geometric series over here, and I'm just going to write down what's our geometric series formula. We learned this in our last topic, guys. Okay, so if I had to do S10, okay, my T1 is 64. My common ratio is 1/2 to the n minus 1 over 1/2 minus 1. Now, guys, I'm going to just go ahead and plug this into my calculator here. Guys, in this case, I'm going to leave the decimal. I'm not going to put this as a fraction up here. But I got 127.875. Okay. The second question is, what about S20? And I'm just going to do the exact same thing, except my n value is now 20. It's not 10. So if I'm just going to go ahead and modify this guy over here, guys. I'm just doing this with my calculator, guys. If you need practice on this, take a look at the previous video. But the same thing that we did before. Now this answer over here is 127.9998779. Okay, so the idea, guys, so when I get up to S20, I got 127 point this number over here. Let's see what we get for S infinity, and here's how we do it. If I have S infinity, that would be T1. Let's back up for a sec here. Sorry. T1 is 64, so I'm just going to put in a 64 for this question. My common ratio is 1/2 to the infinity. Now, guys, this I'm going to say is very loose math over here because infinity is not a number, but it's kind of proving what's going to happen over here. Now, guys, the idea is, what's this answer over here? 1/2 to the infinity is infinitely close to 0. Okay, the guys over here, it's never actually equal to 0, but it's going to be infinitely close. Like in other words, guys, like it's a point where you can't get any closer to 0 as n goes to infinity over this. Okay, so if this guy's equal to 0, doesn't that mean makes sense? It's going to make it 64 times 0 minus 1 over 1/2 minus 1 is negative 64 over negative 1/2, which equals positive 128. So, and I think you can kind of see, guys, that when I did S10, I got 127.875. When I did S20, I got 127.9998779 over here. So hopefully you see, guys, that these answers are getting closer and closer and closer to 128. When I extend this guy to infinity, the actual answer is 128. So example 32, derive the formula for the sum of an infinite geometric series. Well, here's what it is. For a geometric series, where -1 is less than r, which is less than +1. So r has to be in between these two values. We have S infinity equals T1 over 1 minus r. Okay, and guys, this is the formula that we're going to use for this guy over here. Okay, guys, we'll talk about convergent and divergent for these guys over here. So if I look at this guy over here, if I go 300 divided by 900, I get 1/3. So 1/3 is in between -1 and +1, so that means our infinite geometric series formula applies. So I'm going to say guys, we don't need to write this every time. I'm just going to the first one over here. If you look up to the definition over here, guys, if a series converges on a fixed value and therefore has a sum, it is called convergent. Okay, so in other words, guys, if your common ratio is in between -1 and +1, you're going to have a convergent infinite geometric series. Okay, so we're going to go S infinity equals T1 over 1 minus r equals T1, which is 900 over 1 minus 1/3 is 900 over 2/3 is 1,350. Okay, let's look at the next guy over here. Our R value is 35 over 64 divided by 7 over 16, which is 35 over 64 times 16 over 7. So I'm going to do this with my calculator here. 35 over 64 times 16 over 7 equals 5 over 4. Okay, so in this case, r is bigger than 1. Therefore, the infinite series formula does not work. Therefore, this series is divergent. Okay. All right, 6 minus 4.8 plus 3.84. I'm going to go 3.84 divided by -4.8. Equals -4 over 5. That means this guy does work. Okay, so this is going to be convergent. Okay, because -1 is less than -4/5, which is less than +1. Okay, so -4/5 is in between -1 and +1. So therefore, S infinity equals T1 over 1 minus R. T1 is 6 over 1 minus -4/5 is 6 over 9/5 is 30 over 9, which is 10 over 3. And that's your answer for this guy over here. Example 34. If the sum of an infinite series with a common ratio of 0.25 is 12, determine the first term. Okay, so obviously, guys, 0.25 is in between -1 and 1, so the infinite series formula does work. So that means S infinity equals T1 over 1 minus R. The sum is 12, so that's S equals T1 over 1 minus 0.25. I'm just going to multiply both sides times 0.75. 0.75 times 12 is 9. And there's our first term over here. All right, express the repeating decimal as a fraction using an infinite geometric series. Guys, I don't know if you know this over here, but the answer is going to be 1/9. If you go 1/9 on your calculator, you're going to get 0.1 repeating over here. But show you how this works over here. 0.1 is the same thing as 0.1 plus 0.01 plus 0.001. Okay. If you take any two consecutive terms, we get a common ratio of 0.1. Okay. So in this case, our T1 is 0.1. Our common ratio is 0.1. So therefore, S infinity equals 0.1 over 1 minus 0.1 is 0.1 over 0.9. And if I just multiply times 10 times 10, I get an answer of 1 over 9. All right, guys. So guys, that is it for the topic of infinite geometric series, and this is the conclusion of our sequences and series unit. Hope everything's going well with this unit for you guys. I know there's definitely some very tricky concepts in this unit over here, but please come and see me if you have any questions about this stuff, and I will see you in the next video.